Good morning. So we begin today the section on determinants, a very important section in the course. Take a moment and write down the definition that I already wrote here, and you'll see that I'm going to spend quite some time actually describing how the determinant is in fact computed rather than the formal definition of it. I'm going to give you a little bit of a motivation because as written the definition is quite vague. So I mentioned here that let's establish one thing from the beginning. Those of you who didn't do this before, obviously this is all new, right? So just to make it clear, this notion of a determinant, it's a scalar, it's a quantity or a scalar function, right? It's a real number, and it is defined, this scalar function, this real number is defined on the entries of a square matrix. So a matrix with the same number of rows and columns. So the notion of a determinant is only designated for matrices with the same number of rows and columns. And this function, this determinant is defined in such a way that it describes several important properties of the matrix itself and the structures related to it, like for example associated systems or systems that can be described by that matrix, or topics related to vector spaces, that for example matrices can be used to define how you switch one base to another in a vector space, something we're going to learn later what's that all about. So it's a very important tool that encapsulates some of these important properties. Now, well, not unfortunately, but from a practical perspective, we don't actually go over the formal definition of a determinant. I'm going to use essentially the way we compute determinants to act as a definition if you want. The formal definition actually requires some knowledge of combinatorics, and it's just beyond the scope of this one credit class. So for that reason, we're going to skip the formal definition, and we're going to focus primarily on the properties or the motivation related to this notion of a determinant, and on how we actually compute it. So let's establish, of course, a notation first. So if you have an n by n matrix, a square matrix, the determinant of the matrix A is denoted by det of A, like that, or as we often are going to use, this is just more practical, A between vertical bars. So not to be confused with the brackets when we have the notation for a determinant for a matrix itself. So as an example, if I write it like this, A, B, C, D, I'm referring to a matrix. And if I write the same matrix between vertical bars, this will be the determinant of that matrix, which again is a real number. So I'm going to write down immediately what that is, because the first determinant we're going to learn how to compute is for a 2 by 2 matrix. But I want to give you a little bit of a motivation. So one of the properties of the determinants is that, so one of the important properties we'll talk about quite often is that if the determinant of let's see, so if the determinant of an n by n matrix is not 0, right? So if the determinant is not 0, then the systems of equations described by this matrix has a unique solution. right? So this is one of those very useful properties. And I'm going to mention it from the beginning because we're going to use this property in many contexts throughout the course. So it gives you a quick criteria or tool to establish whether a system will have a unique solution or not before you even solve that system. So if the matrix of the coefficients of that system, so of course this refers only to a system in which you have n equations and n unknowns. So this is of course restricted to the situation in which you have the same number of equations and unknowns, because otherwise you won't have a square matrix. So remember, determinants are defined for square matrices. So I mentioned this from the beginning, from the onset, just to justify why the determinant is defined in the way it is defined. So given this property, so how do we know actually, based on what we learned before, that a system has a unique solution? So imagine, for instance, you have the a system of two unknown equations and two unknowns. Ax plus by equals some, let's say some number m, and then cx plus dy equals some number n. If I were to proceed with the row reduction and bring this system in the reduced row echelon form, if I'm gonna have a unique solution, so if we're gonna end up with a unique solution, then we know that in the reduced row echelon form, right, so starting with the original augmented matrix A, B, C, D augmented by the right hand side, then in the reduced row echelon form, again, provided, assuming that I'm going to end up with a unique solution, one should end up with exactly two pivots on the left side, right? So you have 1, 0, 0, 1, and of course Mn will be different numbers, right? So let's say P and Q, right? Different numbers that will occur from making the row operations. But this is what you're going to end up, right? And then you're going to end up by saying, okay, the solution is x equals p, y equals q, right? That's when you have a unique solution. When you have the identity matrix, when you have as many pivots as the number of unknowns in this 2x2 system. So let's actually proceed to the reduced row echelon form to see actually what happens with the entries of the original matrix A, B, C, D. So how would you come up with the row reduced echelon form? So let's assume, for simplicity, let's assume that A is not equal to 0. Then in the augmented matrix A, B, C, D, M, N, I'm going to have to divide by A. So I'm going to take row 1 and divide it by A. And the first row becomes 1 B over A, and then M over A. Actually, you know, the right hand side of the system, I'm not going to track it that carefully because that's not the point. I'm going to want to focus on the left, the coefficients of the matrix, right, where the pivots are located. And then the second row is C, D, and N. And then on the next step on the reduced row echelon form process, I'm going to have to make a 0 underneath the pivot 1. And so that's achieved by taking row 1, multiply that row by minus C, and add it to row 2. So if we do that transformation, then we have 1 B over A, M over A. And then the second row, I'm going to actually, sorry, let me actually start over from the left because I want to have more space here. So the first row is 1 B over A, M over A. And the second row after this transformation becomes 0 minus BC over A, because I multiply the first row by minus C, and add it to row 2. So that means add D. And of course, the second and the last entry will be what? Minus CM over A plus N. So I'm not going to move on further with the row reduced, with the row reduction. the key thing I want you to focus on, to look carefully, is this entry here. What needs to happen? So what do we need in order to have that second pivot? Because if we don't have a second pivot, we do not have, of course, a unique solution. We want that second pivot, minus BC over A plus D, to not be equal to 0. All right, so just pause for a moment and try to observe what we just mentioned here. If that entry was 0, then in the reduced row echelon form, you would end up with the last row like this, 0, 0, and some entry here on the right-hand side. So then from this point on, there would be two possibilities, right? Either you're going to have 0, 0, 0, and that gives you infinitely many solutions because you don't have a second pivot, so you just solve for the first pivot for x in terms of y. Y is arbitrary, so that gives you infinitely many solutions. Or you end up with 0, 0, and the non-zero entry here on the right-hand side. So that means the system is inconsistent. Right? So in order to have exactly one unique solution, we need this quantity minus BC over A plus D not equal to 0. Now, if we add these fractions a little bit here, so if you combine with the common denominator, I got to multiply by A, the second fraction, I end up with AD minus BC over A, which needs to be not equal to 0. We already assumed, right, that A is not equal to 0. If A is 0, we make an interchange. There are a little bit of different particular cases. But in order for this to not be equal to 0, we also need AD minus BC not equal to 0. So this is my motivation or justification for you at this moment. Why, and let's write it down carefully before we move on the next page. Why, by definition, we use this as a definition, the determinant of a 2 by 2 matrix, so if A is given by A, B, C, D, the determinant of A, which is again the determinant of this 2 by 2 matrix, by definition, or is calculated as A times D minus B times C. So you cross multiply the diagonals, starting with the one connecting the left up corner with the right down corner, and then subtract the product from the other diagonal. So I hope it's very simple. Memorize it from this point on. A 2 by 2 matrix is evaluated. The determinant of it is AD minus BC. So again, because one of the main properties of the determinant related to systems, by the way, that's not the only use of it, but related to systems, the determinant tells you that a system has a unique solution whenever it's not equal to 0, right, for the system associated with that matrix. You can see here the connection in the case of a 2 by 2 system. So in the case of a 2 by 2 system, obviously, if the determinant is not equal to 0, which is AD minus BC, my 2 by 2 system has a unique solution. Okay, so with that out of the way, let's actually proceed and see how we can define the determinant in general for any number of rows and columns, and then we'll follow up with how we evaluate it. So stay tuned for the next page. All right, so let's take actually a quick extra example before we move on, just to make the point. So let's say you have x plus 2y equals 3, and then let's see, 2x plus 4y equals 6. So if you look carefully, the determinant of the matrix of the system, of the coefficients of the system, is 0, 1, 2, 2, 4. 1 times 4 minus 2 times 3 is 0. So indeed, if you proceed with the reduction, row reduction, we're going to multiply the first row by -2 and add. You end up with 0, 0, 0. So this will have infinitely many solutions, right? And then you will simply solve x in terms of y, and then y is arbitrary. right? Now, obviously, if there was a different number besides 6, then you'll have no solutions, because then the last row will end with a non-zero entry. So let's again write down one more time the determinant of a 2 by 2 matrix ABCD is equal to AD minus BC. Okay, so now how do we define the determinant for larger matrices? So for this we have to be patient and make sure we observe all the notions. But let me give you the main idea before we define all the necessary tools. So determinants of higher order, right? That means n by n with n greater than or equal to 3, right? So 3 by 3, 4 by 4, and so on, are evaluated recursively in terms of lower order determinants. It's done using the so-called cofactor expansion, which I'll explain in a minute. But basically the main idea is this. A 3 by 3 determinant is basically a linear combination, summation basically, with coefficients, some precise coefficients. It's a linear combination of 3 2 by 2 determinants, right? So that means once I know how to compute the 2 by 2 determinant, with this cofactor expansion, which I'll define in a minute, any 3 by 3 determinant is essentially involving the computation of 3 2 by 2 determinants. And then the recursion follows the same pattern. A 4 by 4 determinant is going to be the linear combination of 4 3 by 3 determinants. Okay, so I'm mentioning this from the beginning to give you a strong, very strong motivation to actually learn, with a tool I'm going to talk about in a moment, a way to determine, to evaluate these determinants in an efficient manner, because strictly with the recursion definition that I just described here, if you don't use some simplifying techniques, things can get ugly very quickly. Because think about this. Let's say I have a 4 by 4 determinant, right? That involves the computation of 4 3 by 3 determinants. But in turn, each 3 by 3 determinant involves the computation of 3 2 by 2 determinants. So in the case of a 4 by 4 case, I'm going to end up evaluating 12 2 by 2 determinants. So you do not want to do that if there is a choice in the matter. And there is. To save yourself from evaluating so many determinants. I mean, to actually evaluate, to make such a tedious computation. So please keep that in mind. There is a way to avoid this complication, fortunately. But keep this in mind that, conceptually speaking, this is how the definition works. And it stands to reason, right? If you go, in a 5 by 5 matrix, that leads to 5 determinants of order 4, each in turns 4 determinants of order 3, and so on and so forth. So let's go over a couple of extra definitions before we learn how to evaluate it. So the first definition that we're going to need is the notion of a submatrix from a matrix. So a submatrix A sub ij is obtained from a matrix A by deleting or removing row I and column J. Okay, so let's write a quick example. Let's say you have a matrix A given by the entries 6, 2, 6, 5, 1, 2. Just to warn you, and then the last entry, let's say it's 6, 1, 1. Well, let's use a different number just to variety here. So let's say 3, 4, 1. Just for variety here, so I can see the entries clearly. If you're new to this, again, pause and then try to follow up without, without making too much of a mess in the notes here. Because when I say delete the row I and column J, I want you to visualize me deleting this, because if I do this for every submatrix, I'm going to make a mess in the notes. So let's start with A11, big A11, right? So that is the submatrix obtained by deleting row 1. So I'm going to delete 6 to 6, right? I'm going to make a very small markings here, 6 to 6, and then the column 1, 6, 5, 3, right? I'm going to write the matrix again just to make it clear. And then A11 is left with 1, 2, 4, 1. Okay, so let me write the matrix A one more time. See, that's the reason why I don't want to circle the rows and columns that I eliminate for each possible submatrix, because that'll make a mess. So I hope it's clear what we're dealing with here. What about A12? Remember, the row is mentioned first always, and then the column. So now I actually eliminate row 1 and column 2. So 6 to 6 and 2, 1, 4 goes away. You're left with 5, 2, 3, 1. Try to pause the video and try to write the other ones yourself, and then check with me. A13, remove 1, column 3, row 1, column 3, you're left with 5, 1, 3, 4. And you get the gist, I hope, right? Row 2, column 1 goes away. 1 is left with 2, 6, 4, 1. A22, row 2, column 2, you're left with 6, 6, 3, 1. Row 2, column 3, I'm left with 6, 2, 3, 4. And finally, the submatrix is coming from the last row, row 3, column 1, that leaves 2, 6, 1, 2. A32, row 3, column 2, I'm left with 6, 6, 5, 2. And finally, row 3, column 3, that leaves the submatrix 6, 2, 5, 1. Okay, we're not going to have to write that many submatrices, don't worry about it, but this is just to make it clear as a first example. So that's what constitutes a submatrix. And another related definition, a minor, denoted by big Mij, is the determinant of the corresponding matrix, of the corresponding submatrix big Aij. So in our notation, Mij is the determinant of the submatrix Aij. So let's write a couple of examples. Let's say the minor 3, 1 is the determinant of submatrix A3, 1. In my example over there, that's 4 minus 6, which is negative 2. Let's do another one. Let's say the minor 2, 3. That's the determinant of A2, 3, which is the matrix 6, 2, 3, 4. That's 6 times 4 minus 3 times 2, 24 minus 6 equals 18. Alright, so with that out of the way, knowing what is a minor, what is a submatrix, we're finally ready to introduce the determinant, the definition of a determinant, or the way we evaluate it in general, using the so-called the so-called cofactor expansion. All right, so let's stay tuned for the next page. All right, so the matrix, a generic matrix of n rows and n columns, is the determinant is given by the following linear combination, the so-called cofactor expansion. So let's take an n by n matrix, and this cofactor expansion is defined for any row or column for that matter. We'll talk about that in a moment. But take the matrix, pick any row you want, right? So imagine you have the entries here, and at some point you have row I, whose elements are AI1, AI2, ... AIN. Again, it doesn't matter which row you pick. Pick any row. Any column as well will work the same way. We'll get to that in a moment. But just one of them, right? One row or one column, right? Then the cofactor expansion states that the determinant of the matrix A is the sum made of the following entries. So look carefully here. Each term in the sum has three components. There is a signature element, -1 raised to, so you take each entry of the row at a time. So the first element in the summation is -1 to the power row plus column of that element, I plus 1 in this case, right? So starting with AI1. Multiply by the entry in the matrix itself, AI1, multiply by the minor corresponding to that entry, MI1. That is, of course, the determinant of the submatrix obtained from removing row I and column 1. And you continue with the summation and add up the similar terms for the rest of the row. So the next element is going to have the signature component, -1 to the power row plus the column of that element, so I plus 2. So notice that this is essentially means there is an alternance of signs, minus plus minus plus, or plus minus plus minus, depending on whether I plus 1, I plus 2, and so on are even or odd. So each of these elements in the sum, in the cofactor expansions, again are formed by three things. There are three components. The signature component, -1 to the row plus column, the element itself in the matrix, so here comes now AI2, and then the minor corresponding to that element, MI2. It's going to be pretty clear once we get to an example, but for now let's finish up the definition, plus ... all the way to the last one. So -1 to the power I plus n, right, the last element, AIN, times the minor corresponding to that entry. So each of these minors, of course, are determinants of lower order, and then each of them can be evaluated via cofactor expansion. So for example, if it was 4 by 4, you will have 4 minors of order 4, and then each of them will be split into another cofactor expansion on its own. So that's why I'm saying that, of course, it's much better to learn some techniques to simplify matters quite a bit. Now, before we learn how to simplify the entries of the matrix so we can avoid this heavy computation, let's apply the cofactor expansion for one example. Obviously, we're going to choose a 3 by 3 case, which is higher order than 2, but not too big so that we don't waste too much time. Okay, so suppose we have the matrix 1, 3, 2, 0, -2, -1, 3, -4. And let's proceed with the cofactor expansion for the first row, 1, 3, 2. So according to the definition, the determinant of A will be -1 to the power 1 plus 1, which is row plus column number, times the entry itself, 1, times the minor. So remove column 1, row 1. You're left with the minor given by the matrix minus 2, 1, 3, minus 4. Moving on, minus 1 to the power 1 plus 2, row 1, column 2. Entry in the matrix. Now the minor is going to be 0, 1, negative 1, negative 4. And then finally minus 1 to the power 1 plus 3, the actual entry 2. And then 0, minus 2, negative 1, 3. Right? The minor obtained by deleting row 1, column 3. So the first element is, signature element is plus, because it's minus 1 plus minus 1 to the 2, right? So it's going to be 1 times 1. So 1 times the determinant minus 2 times minus 4 minus 3. And then the next one is going to be minus 3, because it's minus 1 to the 3. Determinant is 0 minus negative 1. And then finally plus 2. And the determinant is 0 minus negative 1 times negative 2. That's going to be in the end minus 4 over there, right? So that's 8 minus 3, that's 5. What do we have here? Plus 1, right? So minus 3. And then plus 2 times minus 2, which is negative 4. 5 minus 7, that's negative 2. So the determinant of this matrix is negative 2. Okay. So let's see, the next thing I want to do. Yeah, so I want you to notice something before we move on. So notice, and you can even write it as a remark here. Entry is equal to 0. Make computation much faster. I hope some people already noticed that I could have chosen a better row, right? So I chose purposely the first row so you can see how the cofactor expansion works in general, but obviously if I were to choose one of these rows, the second row would have been better. Why? Well, because that saves me from computing one of these minors. So think about this. If I do the determinant by the second row, the first element in the cofactor expansion, minus 1 to the, let's see, row 2, column 1 now, I don't have to actually compute it, right? Because since the entry of the matrix is 0, I can just skip that part in the cofactor expansion, right? And I can just continue with the second one, minus 1 times to the power row 2, column 2, entry in the matrix minus 2. The minor for that guy is 1, 2, minus 1, minus 4. So I have only two minors to compute. Minus 1 to the power 2 plus 3, the last element. The entry is 1. And then you have 1, 3, minus 1, and 3. Okay, so then let's see if we get the same thing. Minus 1 to the 4th is 1, negative 2. Determinant is minus 4 minus negative 2, that's plus 2. And then minus 3, 1 times 3 minus negative 3. We have 4 minus 6, as expected, minus 2. Okay, that is still not good enough, believe it or not, because if I have, first of all, maybe I'm not lucky enough to have actually zeros in the matrix. But even if you have 1 or 2 zeros, if it's a larger matrix, it might still take quite a lot of time to compute the determinant via this cofactor expansion. The good news, and let's write it here as a main motivation, the good news, there are ways to create zeros. In other words, we can use row operations because the determinant actually behaves in a predictable way via row operations. So the determinant behaves in a predictable way via row operations. So the same row operations that you use to solve systems via the row reduction, via the row reduced echelon form, these row operations can be used to create zeros and ease our computation of determinants. So we can just use row operations to actually make zeros and thus basically evaluate the determinant in a much faster way. So first of all, before I actually show you how this is done, let's move on to the next page actually, because we have to establish first of all how the determinant behaves under row operations, and then how we can use it to actually make the computation much faster. So stay tuned for the next page. All right, so let's describe in a schematic way how the determinants change under row operations. So I'm gonna write here like in a some sort of a column, like some sort of a table. So let's say you have the original matrix in this column. Then I'm gonna indicate the transformation, the new matrix, and then how the determinant changes, determinant property. All right, so you have the original matrix. Maybe the last and the first last comment is not really necessary, but let's say you start with a matrix, an n by n matrix, right, for which the determinant makes sense. Right, so the transformation, let's say you do the transpose. The transpose is when you interchange a column with a row, right? So basically each columns become new rows. I'll show you an example in a minute. And then you have a new matrix B. This is also sometimes denoted by AT, right? The transpose of A. Determinant is the same. So what we learn about matrix by row operations, by the cofactor expansion, that you can pick any row and do the cofactor expansion. By the same token, because of this property, you can pick any column, right? It makes no difference. So you pick any column, you pick any row, the one with more zeros, obviously, right? And then you can do the cofactor expansion by that column, and then you get the same answer. I'll show you an example in a minute. Then another transformation, that's the most important one. So let's say you have the original matrix A, and then the transformation is that you're going to replace a row by the old row plus some constant times another row. It's just the main row operation that you use to create zeros when you obtain the reduced row echelon form. So you do this transformation once, then you obtain a new matrix. The main property is that the determinant is the same. So same determinant. Under this row operation, again, when you change one row with a linear combination of a row plus a constant times another row, then you get right. You get the same determinant. Let's see. There's another transformation. Again, you start with a matrix. You interchange two rows. You obtain a new matrix. The determinant changes the sign, right? So be careful with this one, right? So if for some reason you interchange the two rows in a matrix, then the determinant sign changes. This is actually not used that often, just for the evaluation of a determinant, but if there is a reason to do that, in some cases, you have to be aware of tracking how determinant changes. So things are pretty simple. Interchanging rows and columns, same matrix, right? So here's an example, right? So let's start with 1, 2, 3, 4. Okay, you take the determinant of this 1, 2, 3, 4. That's 4 minus 6. That's negative 2. If I take the transpose, the transpose means that column 1 now becomes row 1. So 1, 3 is the first row. Column 2 becomes row 2. So notice that, again, the determinant is the same. It doesn't change under the transpose. And if I go back to the previous example with the matrix 1, 3, 2, 0, minus 2, 1, negative 1, 3, negative 4, if I go by the first column as the cofactor expansion, so minus 1, so I go by the first column, right? So minus 1 to the power 1 plus 1 times the minor, which is negative 2, 1, 3, minus 4. I'm going to skip already the second entry because it's 0 anyway. And then move on to the last one, minus 1 to the power row 3, column 1, so 3 plus 1. The entry itself, right? In the first case, the entry was 1. And then the minor corresponding to that entry is 3, 2, minus 2, and 1. So I should get obviously the same thing. First determinant is 8 minus 3 times 1. Then minus 1 times 1. And then 3 minus negative 4, that's plus 4. 5 minus 7 equals negative 2. Again, as expected. I purposely choose the same matrix just to convince yourself that doing it with various means, you obviously get the same answer. So let me give you a quick proof with a 2 by 2 matrix why actually the determinant doesn't change under the transformation. One row is another row plus c times another row, right? So via that linear combination, right? So let's say, for example, A, B, C, D, a matrix 2 by 2, and let's modify the first row by adding to it row 2 times x, for example, right? So basically the determinant becomes a plus cx, b plus dx, right? So I multiply cd by x and add it to row 1. Okay, so if you expand this determinant, I hope you see that the effect of the row operation, right? The effect of the row operation on the original determinant of course is AD minus BC. It's cancelled, right? So CDX, CXD, those two quantities cancel. So obviously that gives you the original determinant. So I hope it's clear based on this 2 by 2 determinant that that row operation doesn't change the determinant. That's the greatest part of the whole discussion here. I hope you guys see what this leads to. Since I can make these row operations however often I want without changing the value of the determinant, I can use them to my own advantage to create zeros so that I can actually have an easier time with the cofactor expansion. So one last important remark before we turn the page, which is related to this. If a matrix has a row as a linear combination of other rows, like obtained by multiplying a constant times another row and added it to it, right? Then the determinant is 0, right? So again, we're going to illustrate this briefly with generic 3 by 3 matrix. So let's say you have, for example, a matrix with 2 distinct rows. I'm going to call them x1, y1, z1, x2, y2, z2. And I'm going to make the third row a combination of the first two. I'm going to make it x2 plus cx1, y2 plus cy1, z2 plus cz1, right? So basically, I made so that the third row is the row 1 plus, or row 2 plus c times row 1. Now, if I basically undo this combination, so let's say in this matrix I do row 3 minus c row 1, right? I know that the matrix, the determinant doesn't change based on the properties I mentioned before. So then now the third row becomes just x2, just y2, and just z2, right? Because I have x2 plus cx1 minus cx1, and the same thing for the other entries. Now I have a determinant with two identical rows, and if I make another transformation, row 3 minus row 2, then the consequence of this is that now I have a row with all entries equal to 0. So of course, if I have the cofactor expansion by the last row, the determinant will be 0. So again, that's a crucially important remark to keep in mind when you learn the determinant for the first time. Identical rows, or identical columns for that matter, remember the transpose doesn't change, the determinant is the same, right? Two identical rows, two identical columns, or more generally, one column or one row, linear combination of the other columns or rows, means the determinant is equal to 0. So with that being said, let's move on to actually using these row operations to create zeros and then compute determinants more efficiently. So stay tuned. Yeah, sorry for the interruption because I had the wrong matrix to begin with. So let's start again with the matrix 1, 3, 2, 0, minus 2, 1, minus 1, 3, minus 4, right? The original matrix that we used before as an example. So I already noticed that I already want to use the existing 0 here in the matrix, right? The one in the second row and first column. But there's no reason to be happy with only that, right? We can create extra zeros. The idea is that you can create basically all zeros entries except one in a given row or column. Now, of course, if you can create zeros for the entire row or a column, that means the determinant is equal to 0. But if the determinant is not equal to 0, you should still be able to create as many zeros as possible, basically all zeros except one entry. So for example, the easiest thing here is to obviously use 1 as a pivot in the first row, and then change row 3 by adding row 1 to it, right? You simply exploit the fact that these two are opposite. So if I just add row 1 to row 3, then my determinant is going to be the same based on the property we just mentioned. But the cofactor expansion will have only one term. So 1 minus 1, 0, 3 plus 3, 6, 2 minus 4, negative 2. So now, of course, I'm going to use cofactor expansion for the first column. There is only one term in that cofactor expansion. And then one minor, minus 2, 1, 6, negative 2. And obviously 4 minus 6, negative 2 as expected. So use our operations for by rows or by columns to actually create zeros. And just because you do not have a 1 already, that doesn't mean you should give up, because you could use carefully some row operations to actually create these extra zeros if you look carefully. Remember, you're free to do as many row operations as you want. So here's another example, kind of like the more general case when you have no zeros to begin with, or no ones as a prop, as a pivot. So let's say we have 2, 3, 2, 3 minus 2 minus 2, 5, 3 minus 4. So let's see. Yeah, so what could we do to make we can make a 1 first, and then we can make zeros because of it, right? Below it or above it. So notice I could just subtract row 1 from row 2. So I could do row 2 minus row 1 and change row 2 with this combination, because that will give me an entry equal to 1. And from that I can create zeros elsewhere. So 3 minus 2 minus 2 minus 2, that's negative 5. Minus 2 minus 2, that's negative 4. And then for now, copy the rest. Then I'm going to use this 1 to create zeros below and above it. So I'm going to do row 1, old row 1 minus 2 row 2. And row 3, I'm going to change it with row 3 minus 5 row 2. Right? That'll give me 0 below this 1. Okay, so minus 1 times 2 plus 2, that's 0. 5 minus 5 times minus 2, that's 10, which makes it 13. Minus 4 minus 2, 8 plus 2 equals 10. Middle row stays the same. And then minus 5, 1 time plus 5, that's 0. Minus 5, 25 plus 3, that's 28. Minus 5, minus 4, 20. Minus 4, that's 16. So now again, I go by the first column. Signature element is minus 1 to the power 2 plus 1, row 2, column 1. Entry of the element is 1. And the minor is 13, 10, 28, 16. And that's it, because the other entries are 0. So I have minus determinants 13 times 16 minus 280. That should be equal to 72. Okay. So just for the sake of it, if you are not to do these row operations, let's say you pick the first row, then the price to pay is that you're going to have more minors to compute. And you shouldn't do that, because again, you save a lot of time if you create zeros with row operations. That's the whole idea. 3 minus 2, 5 minus 4. Let's just do it for the sake of it, just to convince yourself that you get the same answer. So we have 2, 8 plus 6 minus 3 minus 12 plus 10, and then plus 2, 9 plus 10, which is 19. So 28 minus 2 minus 3 plus 6, 38. Right, so that should be obviously 72. All right, so another row, actually there is another operation I should mention here. So another property that I forgot to mention. So let's say you have a matrix A, and then you multiply a row or column by a number, let's say C not equal to 0. Then the determinant value is multiplied by that entry. So the new matrix B determinant is going to be C times the determinant of the original A. So in other words, to illustrate as an example, let's say you have the matrix given by, let's say, 1, 2, 3, 4, right? Let's actually make some variation here. Let's say 1, 2, 5, 4. Okay, so then I look at the matrix obtained by this. From this one, when you multiply by a constant, let's say I'm going to multiply the first entry by 7. Or let's say by -3. So 1 times -3, 2 times -3, that's -6. If you look at the determinants of these, so the determinant is 4 minus 10, which is -6. And this one is -12 minus -30. That's 30 minus 12 makes it 18. So notice that 18 is precisely -3 times -6. So it's that multiplier, basically, -3, that you had on the same row. In practice, what happens is that if I have a determinant, in practice usually this property is the other way around, right? It's used kind of in reverse. So let's say I have a matrix with entries 40, let's say 30 and 20, -6, -2 and 4, and then let's say 3, 1, 5. Okay, so if I notice I can pull out a common factor of the entries of a given row, that common factor comes out of the determinant as a factor. So notice I can pull 10 out of the first row, and I can pull, let's say, 2 out of the second row. So the determinant of the original matrix is going to be 10 times 2 times the matrix of what's left. 4, 3, 2, because I pulled 10 out, and then -3, -1, and 2 from the last row. So that allows you, of course, to simplify the entries, work with smaller numbers, right, when you compute the determinant. So you can pull a common factor of a given row or column out in front of the determinant. And then let's say the last remark, I don't think I'm going to start another page. We'll talk about this in more details with the next lessons. There are the so-called diagonal matrices. Let's illustrate with a 3x3 case in which you have zeros below a main diagonal. So let's say you have first entries, let's say you have x1, x2, x3, 0, y2, y3, 0, 0, z3, let's say. Something like that. If you have a diagonal matrix, again, we'll talk about it in more details. I don't want to extend this lesson too long. The determinant is always the product of the elements on the main diagonal, right? It's a consequence of the cofactor expansion and of the fact of the distribution of these zeros. So you have a matrix with all zeros underneath the main diagonal, right? If I were to do cofactor expansion, notice that in the cofactor expansion, by the first column, x1 will have the signature component plus, because it's row 1, column 1, so it's always even. And then when you're done, when you cross out the row 1 and column 1, you have again a diagonal matrix. So you go again by the first column, signature component is plus, y2, and then again when you cross out row and column by that element, you're left with another diagonal matrix, so on and so forth. So if you keep on doing the cofactor expansion in a diagonal matrix by the first column, you always end up in the end with the determinant being the product of the elements in the main diagonal. I'll illustrate this with a nicer setup, right? With a bigger, with the different notations to make it a little bit more suggestive. For now, the focus is on evaluation of determinants efficiently, so that's the focus of today's lesson, and I think that's it for today. We'll see you next time.